The National Electrical Code, or NEC, does not provide a specific definition of a tap based on conductor ampacity. However, Article 310 provides guidance on tap installations. Section 310.15b3 of the NEC 2005 states that taps must be connected to conductors using insulated connectors identified for that purpose. Additionally, taps should not exceed 10 feet in length and must be protected from physical damage. Taps are also not permitted to be spliced. While the NEC doesn't explicitly mandate that a tap conductor have a lower ampacity than the main conductor, it implies the tap conductor's ampacity must adequately support the load it serves. In the given scenario, where number 1/0 wires connect to point C from a main run of number 1/0 wires between points A and B, the connection to point C can be considered a tap if certain conditions are met. Firstly, point C must represent a load, meaning the number 1/0 wires serve a load and do not supply other downstream circuits. Secondly, the tap must be appropriately protected by an overcurrent protective device, or OCT, with a rating matching the tap conductor's ampacity. This OCT can be located at point A, point B, or point C. Thirdly, the tap's length must not exceed 10 feet, and it must be shielded from physical damage. Fourthly, the tap must be connected to the main conductors using insulated connectors designed for this specific application. Therefore, in the scenario presented, the number 1/0 wires leading to point C can indeed be considered a tap, even if their ampacity matches that of the main conductors, provided the aforementioned conditions are satisfied. Meeting these conditions ensures a code-compliant installation. To summarize the key requirements for a conductor to be considered a tap, especially when it shares the same ampacity as the main conductor, consider these points. 1. The primary function of the tap must be to supply a load at point C, and it should not be used to extend the circuit to other downstream locations. 2. An overcurrent protection device, or OCT, should be in place to safeguard the tap conductor. Its rating should be appropriate for the tap conductor's ampacity. The location of this OCT can be at the origin of the tap at point A, along the main run at point B, or at the termination point of the tap at point C. 3. The length of the tap must be carefully managed, adhering to the NEC restriction of no more than 10 feet to minimize the risk of fault currents causing issues before the OCT can react. 4. Physical protection is essential. The tap conductor should be installed in a way that prevents physical damage, either through its location or by using protective materials or methods like conduit. 5. The connection between the tap and the main conductor must be made using insulated connectors that are specifically listed and identified for this purpose. This ensures a reliable and safe electrical connection. 6. Compliance with NEC Table 310.16, along with all relevant notes, is essential to determine the allowable ampacity of conductors based on their size, insulation type, and ambient temperature. This ensures that both the main conductors and tap conductors are operating within their safe thermal limits. 7. Voltage drop calculation should be performed to ensure that the voltage at the load, point C, remains within acceptable limits, typically not more than 3% for power, heating, and lighting circuits, or 5% for feeders plus branch circuits, as recommended by the NEC. 8. Conductor identification is crucial. All conductors must be clearly identified, especially the grounded neutral conductor and equipment grounding conductor, to maintain safety and prevent accidental connections. 9. If the tap is part of a separately derived system, compliance with NEC Article 250 is necessary, particularly regarding grounding and bonding requirements to ensure electrical safety and minimize the risk of electric shock. 10. All work should be performed by qualified personnel who are trained and knowledgeable in electrical safety and the NEC requirements. They should have the expertise to properly install and verify the tap connection. By adhering to these points, the installation of the tap, even with same-sized conductors, should comply with the NEC, ensuring a safe and functional electrical system. The NEC does not explicitly forbid the use of conductors of the same size for taps. It does place emphasis on the protection and proper application of those taps. The crucial aspect is that the tap conductor must be protected at its rated ampacity and must serve a specific load without feeding through to other circuits. The considerations for tap rules involve more than just conductor size. The NEC tap rules, particularly in Article 240.21, address scenarios where conductors are tapped from a main feeder or service conductors. These rules allow for the reduction in conductor size, providing certain conditions are met, primarily focusing on overcurrent protection and the length of the tap conductors. Firstly, the 10-foot tap rule, covered in 240.21 bone, allows a tap conductor to be up to 10 feet long without overcurrent protection at its point of connection to the main feeder, provided several conditions are met. The ampacity of the tap conductor must not be less than the combined calculated loads on the circuits supplied by the tap conductors, and it must not be less than the rating of the overcurrent protective device terminated at the tap conductors. The tap conductor cannot extend beyond the switchboard, panel board, disconnecting means, or control devices it supplies. The tap conductor must be enclosed in a raceway when it leaves the enclosure. Secondly, the 25-foot tap rule outlined in 240.21b2 extends the allowable length of a tap conductor to 25 feet under more restrictive conditions. The ampacity of the tap conductor must be at least 1/3 of the rating of the overcurrent device protecting the feeder or branch circuit conductors from which it is tapped. The tap conductors must terminate in a single circuit breaker or set of fuses that will limit the load to the ampacity of the tap conductors. The tap conductors must be protected from physical damage and enclosed in a raceway. Thirdly, tap rules for specific applications, as found in 240.21c, cover situations such as motor circuit taps, where the tap conductors supply power to a motor. These taps often have specific requirements related to the motor's full load current and the type of motor being supplied. Fourthly, transformer secondary conductor taps, discussed in 240.21b3, provide guidance on tapping conductors from the secondary side of a transformer. The rules are designed to protect the secondary conductors from overcurrents, considering the transformer's characteristics and the load served. Fifthly, feeder tap protection involves ensuring that the feeder from which the tap is made is adequately protected. The overcurrent device on the feeder must be sized to protect the feeder conductors and must also be coordinated with the protection requirements of the tap conductors. When applying tap rules, it is crucial to consider several factors to ensure safety and compliance. Firstly, load calculations are essential. Before determining the size of tap conductors, a thorough load calculation must be performed to determine the amount of current the tap conductors will need to carry. Secondly, conductor ampacity must be considered. The ampacity of the tap conductors must be sufficient to carry the calculated load and must meet the minimum requirements specified in the tap rules. Thirdly, overcurrent protection is key. The tap conductors must be protected by an overcurrent device that is properly sized to protect the conductors and the equipment they supply. Fourthly, physical protection is required. The tap conductors must be protected from physical damage, often by enclosing them in a raceway. Fifthly, proper connections are important. All connections must be made using approved connectors and methods to ensure a reliable and safe electrical connection. Sixthly, local codes and standards must be followed. Always check local electrical codes and standards, as they may have additional requirements or restrictions on tap conductors. The application of tap rules can become complex, especially in larger commercial or industrial installations. Consulting with a qualified electrical engineer or inspector is recommended to ensure compliance with the NEC and local codes. Proper understanding and application of the NEC tap rules is critical for electrical safety and compliance. These rules are designed to allow for flexibility in electrical system design while ensuring that conductors are adequately protected from overcurrent conditions. Ignoring these rules can lead to hazardous situations, including electrical fires and equipment damage. Always refer to the latest edition of the NEC and consult with qualified professionals when working with electrical systems. The NEC provides specific guidelines for conductor ampacity based on several factors, which are primarily found in Article 310. The most relevant sections include Table 310.16, which provides ampacity ratings for insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in raceways or cables, or directly buried, based on ambient temperature and the number of current carrying conductors. There are also adjustment factors for ambient temperature, as described in 310.15b2. This section requires adjustments to the allowable ampacity of conductors when the ambient temperature is higher than 30 degrees Celsius or 86 degrees Fahrenheit, based on correction factors provided in tables 310.16 through 310.20. There are also adjustment factors for the number of current carrying conductors in a raceway or cable, as described in 310.15b3. When the number of current carrying conductors in a raceway or cable exceeds 3, the allowable ampacity of each conductor must be reduced to account for the increased heat generated by multiple conductors. The adjustment factors are provided in table 310.15b3. Continuous loads are addressed in 310.15c. Conductors must be derated when supplying continuous loads, which are defined as loads where the maximum current is expected to continue for 3 hours or more. The NEC requires that the overcurrent protection device be rated at not less than 125% of the continuous load. Equipment termination temperature ratings are covered in 110.14c. The temperature rating associated with the ampacity of a conductor must be selected and coordinated so as not to exceed the lowest temperature rating of any connected termination conductor or device. Conductors with higher temperature ratings can be used, but their ampacity must be based on the lowest temperature rating of the terminations. The NEC also provides specific rules for conductor sizing and overcurrent protection for various types of equipment and applications, such as motors, transformers, and welders. These rules can be found in the relevant articles of the NEC, such as Article 430 for motors and Article 450 for transformers. In addition to the NEC, local electrical codes and standards may have additional requirements for conductor ampacity. It is important to consult with local authorities to ensure compliance with all applicable regulations. When determining conductor ampacity, it is essential to consider all relevant factors, including conductor size, insulation type, ambient temperature, the number of current carrying conductors, continuous loads, and equipment termination temperature ratings. Failure to properly size conductors can result in overheating, insulation breakdown, and potential fire hazards. The NEC requires that all electrical work be performed by qualified personnel who are trained and knowledgeable in electrical safety and the NEC requirements. Improperly installed or sized conductors can pose a significant risk of electrical shock or fire. The NEC guidelines for conductor ampacity are designed to ensure the safe and reliable operation of electrical systems. By following these guidelines and consulting with qualified professionals, it is possible to minimize the risk of electrical hazards and ensure compliance with applicable regulations. To further illustrate the concept of conductor ampacity and tap rules, consider a practical example. Suppose there is a main feeder consisting of number 2/0 AWG copper conductors, which, according to NEC table 310.16, has an ampacity of 175 amps when using 75 degrees Celsius insulation, which is a common termination temperature rating. This feeder supplies power to a distribution panel. Now, we want to tap this feeder to supply power to a piece of equipment located approximately 8 feet away. The equipment has a calculated load of 50 amps. According to the 10-foot tap rule, we can use a smaller conductor for the tap, provided that several conditions are met. Firstly, the tap conductor must have an ampacity of at least 50 amps to handle the calculated load of the equipment. According to NEC table 310.16, a number 6 AWG copper conductor with 75 degrees Celsius insulation has an ampacity of 55 amps, which is sufficient for this load. Secondly, the tap conductor must be protected from physical damage. We can achieve this by running the conductor in a conduit such as electrical metallic tubing or INT. Thirdly, the tap conductor must terminate in a single overcurrent protective device such as a circuit breaker or fuse that is rated no higher than the ampacity of the tap conductor. In this case, we would use a 50 amp circuit breaker to protect the number 6 AWG conductor. Fourthly, the total length of the tap conductor must not exceed 10 feet. In this example, the tap is only 8 feet long, so this requirement is met. By following these steps, we can safely and effectively tap the main feeder to supply power to the equipment, while also complying with the NEC tap rules. However, there are several additional considerations. We must ensure that the ambient temperature around the conductors is within the allowable limits for the insulation type. If the ambient temperature is too high, we may need to direct the ampacity of the conductors or use conductors with a higher temperature rating. We must also consider the voltage drop across the tap conductor. If the voltage drop is too high, it can cause the equipment to malfunction. In this case, we may need to use a larger conductor to reduce the voltage drop. We must also ensure that all connections are made using approved connectors and methods. Poor connections can cause overheating and potentially lead to a fire. Finally, it is always a good idea to consult with a qualified electrician or electrical engineer to ensure that the installation is safe and compliant with all applicable codes and standards. While the NEC provides a comprehensive set of rules and guidelines for electrical installations, it is not a substitute for professional expertise and judgment. Electrical work can be dangerous, and it is essential to take all necessary precautions to protect yourself and others from harm. The use of insulated connectors identified for the purpose is critical when making tap connections, as mandated by NEC Section 310.15b3. These connectors are designed to provide a safe and reliable electrical connection between the tap conductor and the main conductor. They ensure proper insulation, prevent accidental contact with energized parts, and minimize the risk of short circuits or ground faults. There are several types of insulated connectors available for tap connections, each with its own advantages and disadvantages. Some common types include split bolt connectors, insulated piercing connectors, and crimp connectors. Split bolt connectors are a traditional type of connector that consists of two houses that are bolted together to clamp the conductors. They are relatively inexpensive and easy to install, but they can be bulky and may not provide the most reliable connection. Insulated piercing connectors are designed to pierce the insulation of the main conductor and make contact with the bare conductor. They are quick and easy to install, but they may not be suitable for all types of conductors or insulation. Crimp connectors are installed by crimping them onto the conductors using a special tool. They provide a reliable and durable connection, but they require the use of a crimping tool and may be more expensive than other types of connectors. When selecting insulated connectors for tap connections, it is important to consider the following factors. Firstly, conductor size is important. The connector must be sized appropriately for the conductors being used. Using an undersized connector can result in a poor connection, while using an oversized connector can damage the conductors. Secondly, conductor material is important. The connector must be compatible with the conductor material, such as copper or aluminum. Using incompatible connectors can result in corrosion and a loss of conductivity. Thirdly, insulation type is important. The connector must be compatible with the insulation type of the conductors. Using incompatible connectors can damage the insulation and create a safety hazard. Fourthly, environmental conditions are important. The connector must be suitable for the environmental conditions in which it will be used. For example, if the connection will be exposed to moisture, the connector must be waterproof. Fifthly, listing and labeling are important. The connector should be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or all. This ensures that the connector has been tested and meets safety standards. Proper installation of insulated connectors is essential for ensuring a safe and reliable electrical connection. Follow the manufacturer's instructions carefully when installing connectors and use the appropriate tools and techniques. Always de-energize the circuit before making any connections, and wear appropriate personal protective equipment such as gloves and safety glasses. Insulated connectors are an important component of safe and reliable electrical installations. By selecting and installing connectors properly, it is possible to minimize the risk of electrical hazards and ensure compliance with applicable codes and standards.